Thank you very much, Mr. Chairman. So today I will talk about augmented Skew symmetric system for thin film flows. So maybe you know what is a thin film flow. I will try to explain what I mean by augmented formulation, and I will try also to explain what is a Skew symmetric system. So first of all, I would like to make reference to two papers that we have published on this subject. So if you want to know more about this, you can look at these two papers. The first one is very mathematical, whereas the second one is much more easy to read. So first, I would like to give credit to my collaborators. First, the mathematicians at our university, Laboratoire de Mathématiques, Didier Brèche and Marguerite Gisnon, who did most of the calculation, and Jean-Paul Villa, Pascal Noble, and Frédéric Couder from l'Institut de Mathématiques de Toulouse, who have contributed to this general augmented formulations. And I would like, the main contributors are Gaël Richard and Nicolas Sellier doing their postdocs at our university. So what is the motivation? The motivation is when you look at what is a thin film, the main trouble it comes from surface tension because it introduces a third order operator. So if I call K the curvature, which is here, which is already a second order operator, complex one, which depends on the film thickness H. The surface tension terms is generally the gradient of K, so it's a third order operator. And this operator is not very easy to implement in the numerical codes because it's third order, so very high order derivatives. So generally, people use only a Cartesian grid, which has limitations in terms of what you can do in terms of geometry. And also, there is a strong limitation on the time step you can use. So people use instead generally linearized formulations, so long wave formulations, where in fact the curvature is approximated by the Laplacian of the film thickness depth. However, in some cases, like this one, for instance, when you have drops, you would like to take into account the full curvature. First, because you want to be able to recover the shape of a drop at rest, and also because when you have contact lines, close to the contact lines, if the contact angle is quite large, obviously your gradient of film thickness will not be small, and this is a problem. So the general framework of what we will try to do comes from two ideas from Van der Waals and his students Cordovec, where they consider an interface as being diffuse. So they consider that there was continuous variations of density between the liquid to the gas phase, and they trace the energy of the surface energy through the gradient of the density. So they introduce some formulations for the surface energy of this kind, and you jump to the sharp interface limit with this formula, where the usual surface tensions is simply the integral of this free energy. Okay, this is quite known. So this leads to what people call capillary fluids. So for capillary fluids, you have an energy which is a function of the density, or the gradient of the density. And if you consider an inviscid limit, you have within the Euler-Lagrange formalism, you get this equation of motion. So first, the mass balance, and second, the momentum balance is this way, where appears at the right-hand side these terms for capillarity. So these equations were derived by Denisser, Casal, and Gouin long ago. And here you have simply also a pressure terms. And the pressure terms is simply the Legendre transform of the energy in this system. So this is a mathematical framework for capillary fluids. And there is a very strong analogy between capillary fluids and liquid films. Because, in fact, if you consider a liquid film with a film thickness H, in fact, you consider that this water depth is viscid limit. Within the Euler-Lagrange formalism, in fact, you recover exactly the equation for capillary fluids, so when the density is in fact the film thickness. So that in fact, the 2D diffuse interface problem is exactly the liquid film problems when you exchange the film thickness for the density. And this comes from the fact that the capillary energy, in fact, is a function of the surface area. And the surface area is a function of the gradient of H, the film thickness, like the gradient of density for capillary fluids. So that we can use exactly the same formalism, and you get exactly the equations that were derived by Denisser for this inviscid. So for this inviscid case, so you have shallow water equations, including surface tension terms in this way. So people refer to this problem generally as a Euler-Korteweg system, isothermal because there is no energy equations here. And we can make this very fundamental by considering these fundamental expressions where phi corresponds to a potential energy, gravity for instance, and there is surface energies here where in fact surface tensions may depend on the film thickness or other parameters. Here we take dependence on the film thickness. Why? Because if you relate it to the case of the capillary fluids, generally surface tension is a function of the density. That's all. So within the framework, we have this pressure terms P. In fact, it's not a pressure for liquid, but it's a pressure in the sense of the Euler-Lagrange formalism, which is this one. And if you consider simply shallow water equations with constant surface tensions, the system is much simpler, written this way, where the energy is simply a function of the surface area, and the pressure P comes from the gravity. So it's not exactly the hydrostatic pressure, it is the integral, because in fact it is a pressure in the sense of the Euler-Lagrange formalism for the system. Now, what is the basic idea we want to introduce for the augmented formulations? So the basic idea is to say, let us introduce a new variable, additional variables, V. On this additional variable V, we'll have the dimension of a velocity. And we will introduce this velocity such that the kinematic energy of this velocity is equal to the surface energy. So if you do that, the energy of the system becomes simply the gravitational potential here, plus this kinetic energy, which is a fictitious kinetic energy. And what is very beautiful in this formulation is that the kinetic energy, the true kinetic energy of the system, varies the same way as the surface energy. Okay, but here we are not writing it exactly as a surface energy. We add a shift, this -1 here. So we shift the reference for the surface energy, and this is my main contribution to this work, so I'm very happy with that. Put it in red because of this. And these very little contributions enable to write bijection between the additional velocity V and the gradient of H, which is the next. So that in fact we can write V as a function, bijection function, monotonous function of P here, P simply referring to the gradient of the film thickness. So here it introduces some prefactor alpha, which is a little bit complex, but not very difficult to implement. And I give these monotonous functions. Therefore, in fact, V basically is exactly the same, in a way, than the gradient of the film thickness. So what do we do next? Next, we will work with the conserved variables, which is here simply the momentum associated to the additional velocity. And we write it as a combination of different functions. And within these functions, this is particularly A, which is the gradient of the logarithm of H. Why would you introduce this? It is simply because if you work with the mass balance, and you take the gradient of the mass balance, you can easily obtain an evolutionary equation for the logarithm of H, for this gradient. And then you multiply by G prime, is this formula, and by step, it's a bit complex. At the end of the day, you find an evolution equations for what you are looking for, which is the conserved quantity H times V. Why we do that from the mass balance? Physically, it's very simple to understand because V, additional velocity, is simply the gradient of the film thickness. So that means that it is only the kinematics. So we modify the kinematic equations for the flow such that to get a kind of momentum balance for the new variable HV. That's all. After doing that, the philosophy is to modify the terms coming from the Euler-Legendre formalism in the momentum balance so that they are symmetric in a way with the terms that appears with these new momentum equations for the additional velocity. So finally, the formulations look like this in a conservative form where we have, as usual, the conserved quantity for hyperbolic conservative law, h being the film thickness, the mass, hq being the momentum, true momentum of the liquid layer, and hv being the momentum associated to these new variables. But the difference with the traditional formulation is that we have a left-hand side terms here, which is written here. And this left-hand side terms is quite involved on this, but in fact it has the form of generalized diffusion terms because it is second orders with respect to the operator. So F and G, I will refer to them. I will explain what is this formulation. But what is very important here is the sign. We have a minus sign here, so that in fact these systems, these two terms, are skew symmetric. They are not symmetric, but skew symmetric. And this is important when we will want to prove that the energy of the system is conserved. So here are F and G. F, in fact, is a tensor, and G is a vector. They are a bit complex, but well, it's manageable still. And in fact, there is this very nice theorem that can be proved by the mathematicians, not me. If V at initial times corresponds exactly to the gradient of the film thickness, at later times it will still be true if we solve with our augmented formulations. So we will get exactly the solutions to the initial problems with the augmented formulations. And this is, but the main thing here is, which is not very simple, is that we need regularity. And so that may introduce some problems where we will deal with contact lines. Okay, so, but still. So the energy balance, we get the energy balance very easily by taking the derivatives with respect to the conserved quantity of the total energy. So that enables to write entropic associated variables. We multiply the equation of motions by these entropic variables, and we integrate, and we get this evolution equation for the total energy. And you can see that this total energy is conserved because it is the divergence of a flux, basically. And it's true because these two terms can be written due to the fact that in the primitive formulations we have symmetric terms here. Otherwise, it doesn't work. So that the beauty of this work is that we really need the symmetry between the formulations for the momentum balance, the true momentum balance, and the additional variables. And this symmetry is obtained because we take variables which are physically the same dimensions, velocity. So the symmetry of the equations have some implications within the numerical implementations. And then we have implemented implicit explicit scheme. So the first step is very classical for the hyperbolic part. And the second step is semi-implicit for solving the surface tension terms at the right-hand side. And we did it this way, which is semi-explicit, so that this system becomes linear for the unknown for the velocity. Because in fact, since there is zero here, we can solve the film thickness at step n+1 directly within the first. And therefore, this system is very easy to solve numerically because it is a simple linear system. And what is very beautiful in this work is that at the end of the day, we get a classical CFL condition for this system. Generally, with surface tensions, you get a very drastic limitation for the step. Here is only the classical CFL conditions for hyperbolic system. No more than that. So it's very, very efficient system of time. So we try to test that. We did a 1D numerical test, very simple. We take an horizontal layer of water, inviscid one, and we put a Gaussian perturbation at the top. Because this is localized disturbance, due to the velocity of the water waves, the shallow water waves, you can see that K here being the wave number, the capillary waves will be very fast. So we have to be a little bit cautious. So we take a CFL number 10 to minus 2. CFL number is based on the maximum eigenvalue of the Jacobian of the hyperbolic system here. But that works very well. So this is the wave we obtain in 1D for the linearized capillarity. For the full capillarity, the non-linear one, you can see the difference. There are quite some difference. And what is very interesting here is that you can see that if you use the linearized capillarity, you overestimate the amplitude of the capillary ripples at long distance from the initial perturbation. So this is the difference between the two elevations. So you can see this is quite important difference, and even at long distance. So taking into account the full curvature is quite important in that case. And this is also the velocity in the x directions on the normal velocity v here. So you can see also for the velocities there are quite some effects. And so we did the same in 2D. You can see that, and it works very well, very efficient scheme. And you can see also in 2D you can see that with the linearized surface tension, you overestimate a lot the amplitude of the ripples. Very obvious here. So we did some conversion tests on our system. For the first step is only one order. For the first step we take either a first order step or a muscle method, which is second order. So we can see that with the muscle method, the convergence is much quicker for the film thickness. However, if we look at the velocity here for number of nodes which is larger, we can see that on the velocity we cover at the end first order simply convergence. And this convergence is only first order because, in fact, of the second step, which is simply Euler implicit, so first order in time. So there is nothing more there, but in fact we have a quite good convergence of the numerical system. So let's try to apply this to a falling film on an inclined plane system. So in that case, we used some equations that were derived by Gael during his postdoc at the lab within a conservative form. And this is conservative form. You have these terms here in the special terms, generalized special terms, which is h over 5, which is simply here to guarantee that the system is consistent in terms of the long wave expansion parameter. And the main difference between what we have previously done is that here we include also the effect of viscosity. So first, the viscous drag at the wall, and second, the viscous diffusion terms, which is some like viscous diffusion terms. So this is the curvature terms. So if we include curvature as usual, it will be here, the surface tension terms. So if we use our augmented formulations in 1D, we get the red terms here, plus this additional momentum balance for the additional velocity v. So we solve the two. You can see the difference of respect to f and g easily for the linear curvature. So f and g is functional, are very simple for linear curvature, a little bit more complex for the full curvature, but it's nothing very difficult there. So we computed traveling wave solutions by time integration with the periodic boundary conditions, and we compare them to the same solutions we can obtain by continuation method. So the two agrees very well. So you have the profiles of the waves with the accumulations of capillary ripples preceding, in fact, the main hump. This is the main hump, and at the front of the waves is capillary ripples. So if we zoom in, you can see the difference in terms of the capillary waves at the front of the wave with or without full curvature. We can see that if we include the full surface tension terms, with respect to what is classically done for falling film, we have not much effect. Simply we do dump more the capillary ripples. Okay, so we also tried to simulate shear-driven drops. So this is a drop, seaside drop, which is sheared by a constant shear stress. And the system of equations we solve is a little bit more involved because there is a new equations for phi, which is the correction terms, which guarantees that the system is well posed and consistent in terms of the asymptotics, but this is not very important terms. The important terms here is we add some pressure, some dejoining pressure terms here to model the contact length. So I will skip the details, which is very classical, and I'll show simply some numerical experiments where we have a seaside drop shear, and here there is you can see that the top T forms elongate and forms an elongated drop. Yeah, so this is the simulations that we obtained. So we have done the same, but this time by considering an hysteresis between the front and the back of the drops. And you can see how the dynamics changes and the shape of the drops changes due to the hysteresis of the contact angle. So this is the difference in shape between the two. And I will conclude here by saying first that our homeotic formulations enable us to exchange the third order complex differential operator for the surface tension terms with a generalized diffusive operator. That we have also obtained an efficient IMEX scheme to solve this system. And that in fact we have as a perspective we want to apply these techniques for falling films, but the main point here is that it's difficult to get accurate system in conservative form. So we are trying that. Still in progress. So thank you very much for your attention.
Long live India and France friendship.